Here are solutions to homework set number 5 for ECE 111. This homework set looks at renewable energy. Basically solar and wind. Can you take data from NDON that's got the hourly wind data, hourly solar data for different places in North Dakota, and calculate using Matlab. Is solar energy a good investment in Fargo, North Dakota? Is wind energy a good investment in Fargo, North Dakota? So the first problem is looking at solar. If you go to eBay, you can find kits to basically get a turnkey solar system for your house. This one, for example, is a 13 kilowatt solar system for $18,000. Is that a good buy? Well, one way to analyze it is go to NDON. NDON is a website hosted by the Soil Sciences at North Dakota State University. With it, you can get hourly data for probably like 100 different locations across the state in Minnesota. Well, in this case, I'm going to go to NDON, pull up the hourly data and the solar radiation. So this is kind of what that looks like. Go to this website. So this is the NDON weather site. We go on weather data. Let's do hourly data. Pick your favorite location. Like let's do Fargo, North Dakota. And for the first problem, it's going to do, well, let's see. There's wind speed, air temperature, solar radiation. That's what I want. For the last 2 weeks, let's say. There's your data. Switch to metric. Export to CVS file. And I can pull that data and throw it into Matlab. So once you get that data, what do you do with it? Well, in Matlab, I can sit there and say sun is paste, take all the data from the CVS spreadsheet, copy it into Matlab, end of matrix, find out how many data points I have. I had 672, and then plot. I guess hour is the first column, megajoules is the second column. So if I do that, here's what the data looks like. That's the solar intensity in Rugby, North Dakota from September 1st, 2023 to September 28th, 2023. Okay, it's actually probably 2024, but whatever. I got the solar radiation data for, I guess, 4 weeks. Once I have that, I can start doing some analysis. Let's calculate how many kilowatts I would generate from these solar panels. Now there's 32 panels in that kit from eBay. Each panel has an area of 2 square meters, and the panel efficiency is 20.5%. From that, calculate the kilowatts. Well, I've got the energy density in megajoules per square meter. Doing some unit conversions, 1 megajoule per square meter, my area is 64 square meters. There is 1 million joules in a megajoule. There are 3,600 joules in 1 watt hour. There are 1,000 watts for each kilowatt. Efficiency is 20.5%. Multiply it all out together. 1 megajoule per square meter equates to 3.64 kilowatt hours over 1 hour. So once I get the solar radiation, that's megajoules, convert to kilowatts, and plot it, this is how much my solar panels would produce if I installed them in Rugby, North Dakota, based upon this data. Well, that's in terms of kilowatts. If I want to know the total energy in kilowatt hours, that would be the megajoules times 3.644, the constant just calculated. Add them all up. The width, I'm sampling it every hour, so width times height is just the height times 1. Sum of the kilowatts gives you kilowatt hours. I would produce 1,356 kilowatt hours over those 4-week spans. Now, to determine the value of that, it kind of depends where you are. If you assume Xcel Energy's time of day metering and net metering, I get 15 cents per kilowatt hour between 9 a.m. and 9 p.m., 2.5 cents otherwise. So I can set up a variable called peak. This is 1 if I'm between 9 a.m. and 9 p.m., or 2100 hours. Off-peak is opposite of that. It's 1 if it's not in that time frame. If I'm during peak hours, it's the kilowatt times peak. This is 0, 1. Is it peak or is it not? During peak hours, I get 15 cents. During off-peak hours, I get 2.5 cents. Add them all up, I would produce $201 worth of electricity. Now, the number of pounds of coal I offset, each kilowatt hour, it takes 1.78 pounds of coal to produce 1 kilowatt hour. That's at the Milton Young coal plant in North Dakota. The solar panels offset 2,400 pounds of coal. That's 2,400 pounds of coal that didn't have to be burned to power my house. Finally, do the solar panels pay for themselves? Well, one way to do that is find how many years it takes to pay off the solar panels. They cost $18,000. I am producing, $201 over 4 weeks. So that's dollars per day, 365 days per year. Assuming every day is just like that month, which is kind of a bad assumption, but let's go with it. Assuming every day is just like April of 2023, it will take 7.19 years for the panels to pay for themselves. So kinda. Rule of thumb in business, if there's a 7-year payoff, it's a no-brainer, you do it. This one's kind of marginal. Well, if you get a discount, like take a 30% tax credit, then it's a good deal. If you include installation costs, then maybe it's not a good deal. So maybe, maybe not. This is actually kind of crude analysis, just using 4 weeks of data. But kind of the point is, using Matlab, given data, I can analyze it. With NDON, I could actually go back 10, 12 years and see how the panels would do. I'd probably want to do that if I was investing $18,000. But for the homework set, 1 month data is good enough. You kind of get the idea of how to use Matlab. Okay, so that was solar energy. If you go to wind energy, I can do the same thing. Go to NDON, I can pull up the wind data. So copying the wind energy for 4 weeks, pick your favorite spot. I think I chose Rugby, North Dakota one more time. I can copy and paste that data into Matlab. With this, once you get the wind speed in meters per second, I can then plot. This is collected on an hourly basis, hour 1 through 672, divide by 24 so you get days. Plot the raw wind data versus hour, or day. And here's what it looked like. Between November 2nd, 2023 and November 29th, 2023, this is what the wind was doing in Rugby, North Dakota. Kind of neat thing about the internet is you have access to data like this. Given that data, I can start doing some analysis. Suppose I took a Vesta 163 megawatt wind turbine. How much energy would that produce? Well, the first thing I need to do is come up with a power curve. That'll convert wind speed to kilowatts. Well, this is from the datasheet brochure for a Vesta wind turbine. Come up with a Matlab function that curve fits this. So I tell it the wind speed, it'll spit out kilowatts. One way to do that is to just take the data, throw it in a table. Here's x and y. Let's do a cubic curve fit. My basis is just x cubed, x squared, x and 1. Here's my output. Let's do a least squares curve fit. And just like before, that's inverse of b transpose b, b transpose y. Those are my constants. Now my curve fit. If the wind speed is less than 3 meters per second, I output 0. If it is more than 13 meters per second, I output 4,500, the eclipse. And otherwise, it's my curve fit. And just for fun, let's plot the curve fit versus the, well, plot the power curve and in red, and plot the curve fit in a dot. To check, I can sit there and say, let's have the wind speed go between 0 and 15 meters per second, calculate the kilowatts based upon the power curve, and see what it looks like. So the blue line, or the solid line, is the power curve. The dotted line is my curve fit. Seems to match up pretty well. Okay, so given that, I can now take my wind data and convert to kilowatts. Now, NDON measures the wind speed at the ground, like 6 feet above the ground. I want to actually move it up to, I think it was 180 meters. The conversion constant, as you go up in height, wind gets stronger. It's about 2.2. That's from Wikipedia. So take the measured wind speed at 6 feet, multiply by 2.2. That's roughly the wind speed at 180 meters. So convert that, plot it, and this would be the energy I'd produce in kilowatts over those 2-week spans, assuming, well, a lot of assumptions. Assuming a vested wind turbine, assuming that wind speed data, assuming you scale it to 180 meters. Okay, so there's the energy produced by a wind turbine. Once I get that, I can start doing some analysis. It takes about 1.78 pounds of North Dakota lignite to produce 1 kilowatt hour of electricity. The total energy I produced, is add up all the kilowatts, is 1.3 million kilowatt hours. Big number, that's just one wind turbine. Equating to 2.3 million pounds of coal. So over those 28 days, that single Vestas wind turbine would offset 2.3 million pounds of coal. Question 8 is saying, is this a good investment? Assuming it cost $5 million to build this wind turbine, and assuming the value of electricity uses Xcel Energy's time of day metering, how long does it take for the wind turbine to pay for itself? Well, I'm going to take the time, mod 24. It's going to give you midnight throughout the day. If the hours are between 9 and 21, it's during peak hours, 15 cents. Otherwise, it's off-peak hours. During peak hours, the electricity is worth 15 cents. Off-peak hours is worth 2 cents. Add them all up, and that wind turbine produces $134,000 over that 4-week span. The time it takes the wind turbine to pay for itself is the cost of the wind turbine divided by dollars per day. So dollars over 28 weeks, over 28 days, times 365, that's gives you dollars per day. Or it converts it to years. 3.3 years. So the wind turbine takes about 3.3 years to pay for itself. Again, based upon data over 4 weeks, assuming the wind's the same as it was over that 4-week span. If actually we were going to build a wind turbine, you'd take a longer set of data. But anyway, going with it, using this data in Matlab, I can calculate how long it takes for the wind turbine to pay for itself, about 3.3 years. That tells you that wind energy actually is a pretty good deal. So that is homework set number 5 for ECE 111. Kind of the point behind this is the previous homework set was kind of mentioning that ice is melting, temperatures are going up, CO2 levels are going up. Sounds bad. There is a way around it, and that's kind of good for us electrical engineers. You can use solar, you can use wind. That's jobs for us. You can also use electric vehicles. All of them help combat climate change, help reduce the CO2 going into the atmosphere, and they're big numbers. Plus, you get jobs for electrical engineers. The other thing this homework set kind of shows is with Matlab, Matlab is really powerful along with the internet. With the internet, I can start collecting data and see what's the wind do over a 4-week span. With a little bit of analysis, I can calculate how much energy would a wind turbine produce. I can start doing things and calculating how much is that worth, how much revenue would that generate. All things you can do in Matlab. Matlab's a pretty powerful language. So that's homework set number 5 for ECE 111.